time, not so much during my talk, I've been during Professor talk, and yesterday evening during tutoring session there was this discussion of the notion of representation in quasi-simple, Banach space representation in quasi-simple, and I look at Harishchandra's first paper on representations of Banach space, and actually he has two conditions. One condition is called permissible, and this deals with groups with infinite center, because in that paper Harishchandra goes from connected semi-simple E group to its universal cover, and this universal cover can have infinite center, so this is permissible, and then quasi-simple means permissible plus existence of infinitesimal character. So what I called ZG finite includes this notion of Harishchandra module attached to quasi-simple Banach space representation of the group. So this is clarification of terminology, and this also explains the remark Parthasarathy pointed out during his talk, Logan's remark from Atlas seminar, when he said that quasi-simplicity is important, ZG finite is important, admissibility will follow for our GK module from the theory. And I'll try to explain this maybe today or at the beginning tomorrow. So now let's go to any questions about this. So stop last time. We were just considering modules over U theta, where U theta was quotient of U of G with respect to some ideal I theta in the center, so this is maximal ideal. And which corresponds to Weil group orbit theta of some lambda. And then we define two functors, functor localization functor, which goes to the category of quasi-coherent d lambda modules on the flag variety, and a functor of global section which goes back, and these two functors are joined to each other. And then, so I have to now make the statement from last time precise. We say that lambda is anti-dominant if for any positive root in abstract root system sigma of our pair of our Lie algebra G, alpha check lambda is not a positive integer. So this is anti-dominance, and under this condition we have the following theorem of Bailinson and Einstein, which says that for any V in NQC of d lambda, any d lambda module V higher cohomologies of V I equal to 0. So this implies that in this case, this functor gamma is exact if lambda is unknown.
This algebra u theta is finite dimensional, no?
No. It's an infinite. I mean, it's your I theta is the maximal ideal of a center. So, for example, for SL2, you can take the ideal generated by a Casimir, and then the quotient out. This is infinite dimensional.
The only modules are trivial infinitesimal character. So
But in this example, the modules are a trivial infinitesimal character, and they can be, say, SL2. Trivial representation, and but also discrete series.
that's all.
For Harshadra modules, yes. But this is here we do not have k actions, so there are this huge number of such modules we know nothing about, and we won't learn too much from this theorem before we specialize this to Harshadra.
This algebra is not finite dimensional?
No.
Is there a model for this algebra?
No, not really. I mean, it depends very much on theta. For example, this algebra has finite homological dimension if theta is a regular order. If theta is singular, its homological dimension is infinite. So it's. Thank you.
Sorry? Kx upon x minus lambda is finite. Kx of x minus lambda.
In a way, Harshadra homomorphism just gives you something in H, but so any and bar, say, in particular basis, stay there. So it's no way that this can be finite dimensional. What? Antidominant means that this lambda, when you apply a dual root, is not a positive integer. So you get some picture like this, say in A2, and then certain lines are out. But for example, if you look at the negative chamber, then these lambdas are allowed.
Basically, something which is not just coming from the place for white chamber.
I mean, it's bigger set, but it's enough for our purposes to do exactly what you suggested, to look at the real part sits inside, say, negative chain. Yes. So this implies, as I said, that the functor of Roma section is exact. So let's see what this actually means. Let's take a module V and let's take its free resolution. Or actually, I can just take the two terms. So let's take a look at this exact sequence. And I can tensor this by d lambda or u theta. Since I'm tensoring, the tensor sequence will stay exact, and we will get the lambda j goes into d lambda I goes into the localization of V. Remember, tensoring by this is just the localization at lambda. So this is an exact sequence which you get by localizing, if we apply global sections, we will get u theta j u theta I and gamma x delta lambda e is goes to 0. Now, the adjoint, here you localize and take gamma. So this is one of adjoint morphism for this joint pair of functors. And they are these dotted arrows. And these guys, this follows from the theorem about global sections of delta lambda, which I mentioned last time. So these are isomorphisms, so this thing has to be an isomorphism. So under here, of course, I use the fact that my lambda, so I should stress that lambda is anti-dominant. To conclude that this is exact. So if this is exact, then this is the same thing as the top one. So these two guys are isomorphic. And what does this mean? This means that if you localize and apply gamma, then you get back your margin. But, so what about the other adjointness morphism? So this is if you apply gamma on x v, and then you localize. In this case, so this is tensori of global sections with d lambda. This clearly maps into V. And this can have some co-kernel and some kernel. So the first remark is that if these two guys are 0, this will tell us that the other adjointness morphism is an isomorphism, and these two categories are equivalent. So if you like formal category theory, you can say the following: consider the category of quasi-coherent d lambda modules, and consider the subcategory Q, say script Q, of d lambda modules with no cohomology. So not even global section Spanish. If you look at, say, in SL2, your fiber height is pi 1, you have Sayre's twisted sheaves which align bundles, and the U minus 1 has no cohomology. So this really, such modules exist, and then you can quotient this category by this category Q, and quotienting means, in this particular situation, so this is a abelian category, this is a abelian subcategory, this means that you declare that morphisms where kernel and co-kernel zero have no cohomology are considered isomorphisms, and this is exactly what happens in this case, because, I should continue this, let me apply gamma to this, and we are in anti-dominant situation, so gamma is exact, so I get 0, gamma x k goes into gamma x delta lambda gamma x v goes into gamma x v goes into, let me just, gamma x c goes into 0. Now, if you look at what we just proved, these are joinless morphisms, localizing and taking low obsession appear here, and this is isomorphic to E. So these two guys cancel out, and this becomes the identity map, essentially. So this is an isomorphism. So the conclusion is that in this short exact sequence, not short, this exact sequence, that gamma x k and gamma x c are objects in Q. So if I portion this out, then this becomes an isomorphism. So the first remark, which is important for in lots of situations, is the theorem that MQC d lambda quotient with Q is in general equivalent to, if lambda is anti-dominant, with mu theta. Because we are in anti-dominant situation, so we know that I'm assuming this theorem. Yes. A consequence. So if you are an older representation theorist, then there was this Zuckerman functors people were discussing. When you take a representation and translate it inside wild chamber, and there was a statement which says when you push it to the wall in an irreducible representation, you can get either an irreducible representation or 0. And this is exactly the statement here, because Zuckerman translation corresponds to twisting to a line with a line bundle, and when you push things to the wall, then to see what gamma does, you have to portion out this. So what can happen is that certain irreducible objects vanish, and like in this case in SL2, or they stay irreducible. But, let's see. There is a companion theorem, which, if there is interest, I can show the proof in the tutoring section. I think I prefer not to, which is very similar. If you try to do it, you will easily figure out how to do it. That if I'm sorry. first statement will take some effort, but the consequence I will mention. So this is theorem B. If lambda is anti-dominant and regular, so this is additional condition, then V is, so in MQC, V lambda is generated by global sections. Gamma X. And this implies that if my global sections vanish, then the sheaf is generated by 0, so the sheaf has to be 0. So this Q, in this case, is 0 subcategory, and you get that this is equivalence of categories. Again, let me point out that this is the proof of these two theorems is very simple. It follows by some tricks from Sayre's theorems from FAC. Sayre proves if you have a coherent OX module on, say, in this case, in flag variety, if you twist it by a line, an ample line bundle, too many times, you will kill higher cohomologies, and you will get that the OX is twisted OX module is generated by global sections. Using the facts that we are dealing with sheets of differential operators, there is a way to go back and prove this, that we do not just have vanishing theorems and generation theorem at the limit, but for all lambdas satisfying these conditions. So it's purely a formal proof involving tensoric with finite dimensional representations, and I mean, again, we can discuss this during the tutoring session if there's any interest. But for our purposes today, we want to go a step further in this formalism. We want to apply this to our GK modules. First of all, here, I will replace a note by its complexification. So, I mean, this was discussed in Raghunatha lectures, more or less explicitly at some point. So basically, the reason why we need to do this here is because we have to work in the same category, in algebraic category over C. So real groups just do not fit, so we take this K. And then we can consider the category M U theta K these are our GK modules now. Of course, there is a natural equivalence of categories in our U theta K naught module of this K module because the representations extend to K, so I'm not just doing nothing interesting on this side. And here I will also put finitely generated so that I'm in our category I was denoted by A in one of previous lectures. If I put finitely generated here, then even in this setting, then we end up here in the category of coherent d lambda modules, but coherent as d modules, not they're quasi-coherent as O modules. So when we do the localization and have a function of global sections, I end up in coherent d lambda A modules. Of course, it's quite technical to define objects here. I mean, this is standard in algebraic geometry, but I don't want to dwell too much about this, but just use your intuition thinking what this should be. These are rules which admit algebraic action of A. If you're interested, I can give you references for this. And this is an equivalence of categories. And since we think about this as Harish-Chandra module, I will refer to those as Harish-Chandra sheets. I mean, I don't know if Harish-Chandra would approve this name because he once told me that he doesn't know much about sheaves, sheaf cohomology. But then, by accident, I discovered that actually he was reading Gottman's book on sheaf theory. So he was definitely had some interest in this. And what is amazing, and this is the next step I want to explain, but I cannot resist to tell you this now because you will see how this answers the questions we discussed before. There is a theorem which says that Harish-Chandra sheaves are of finite length. I mean, this category is an abelian category, as you see, so we can talk about irreducible objects and finite length objects, and they are all of finite length. So, if you believe into this and use this version of the theorem, these objects are of finite length. If you apply functorial global sections, you will hit all, say call them Harish-Chandra modules. I mean, some irreducibles, some modules can disappear, but you will get everything in the image, and therefore everything on this side will be on finite length, and this is the theorem I claimed first up. So this is a proof of this statement modulo this D modulo result, which I will discuss at the moment. This makes completely clear what is actually going on in finiteness, because you can vary groups. You can, of course, this would be a silly proof for this, but if you consider highest weight modules, then you can take their highest weight modules with respect to certain partan, and we have a Borel, and we have N. So from Lie algebra N, you can construct corresponding unipotent group N, which acts on your highest weight modules. And you can interpret this category as a category of, say, U of G N modules, and you can play the same game we play and go to this category, and then you localize, and the same geometric argument will prove analogous theorem and prove that highest weight modules have finite length. Of course, this is much simpler statement, but for Hertzsprung modules, this is hard. And so, I mean, the interest in this argument is that it's uniform in a number of different situations. So I want to explain next what is the critical reason why this works. Any questions?
For U theta, this kind of theorem is not true.
Oh.
For MFG U theta, meaning without removing capital K, finite length is...
Oh, no, of course not. You will see the reason why. I mean, this is our next step. So the reason why this theorem holds is a theorem from D module theorem. So let me state a different version of this theorem. Oh, first of all, let me make a geometric statement. I won't prove. Again, we can discuss it in the problem session. If I look at flag variety X, then my group K, complex group K, acts on S. And a geometric fact, which makes everything work, is K acts infinitely many orbits. Again, it's always there is the only written proof of this fact I know is in a paper with Peck, Schmidt, and Wolf in Invenciones on duality theorem they wrote. And the proof we sketched here, there is due to Benson and Bernstein. Joe Wolf claimed that, but I don't know the reference, that he proved this in some other paper. When I mentioned this Borel just laughed and he said, oh, I knew this in the early 50s. So I don't know, but this is a fact. Let me show you that this is something you can easily believe. in the case of SL2R, if your flag variety is Riemann sphere, your K is C star, and the action of K is like this. There are 2 points which are stable under K action, and there is this C star action, which, so there is a map from C star into this C star, which is a twofold cover, which acts on this open orbit. So in this case, we have 3 orbits. And as you will see, so since you are fresh from discussion of SL2R, I can tell you that Harishchandra modules corresponding to discrete series correspond to these 2 closed orbit, and principal series correspond to the open orbit. And this fact that the map from KC to the orbit is a twofold cover corresponds to the fact that there are 2 families of principal series. So this picture gives you some idea why this fact is not too surprising. Now, the second fact
The
is,
general fact that G mod H is a spherical variety where H is fixed point of illumination.
yes, yes, if you
There's
want
that and-
fancy language, this is.
Indeed, I'm sure for real, you know about it in
So, now, why is this fact important? Another trivial remark, if you take the group G instead of K, let's assume that your G naught, we started with its compact. Then maximal compact is K naught, so this K here is Lie group G, is algebraic group G corresponding to the algebra G. So the action on the flag varieties is there is only one orbit. And from this it will follow that only reducible Harishchandra sheaves are homogeneous line bundles. And then this theorem here, the equivalence of categories statement, in this statement tells us that we have Borel-Weyl. This is the amount how far I want to go in Borel-Weyl. But let me, there is a following theorem. If K acts with finitely many orbits on X, so this is again theorem, which implies this. Harishchandra sheaves are holonomic. I mean, this is a notion I have to explain. And holonomic D modules have finite length. So this theorem immediately implies this state. So holonomicity is the magic word.
So this is a statement about K where the modules are in X.
I mean, what is important in the number of orbits is fine. Yeah.
A needs to be a group or
No. No, this is lightweight for highest weight modules in all the situations. It just, as you will see in a moment from the proof, it's very elementary. If you ever took an algebraic geometry course, you will.
X is G mod P.
In this case, yes. You see, I mean, you have to have some connection. And here we have equivalence of categories, but yeah, I think the answer to Arden's question is it's very general, as you will see, because you will see what the proof is. Something which was discussed yesterday on problem session was this notion of symbols. I mean, a sheaf of differential operators has a natural filtration. By degree of differential operator. I mean, you can just think about this gluing procedure, or you can think how I define differential operators. I look at this iterated commutators with n+1 regular functions, and this number n is the bound of degree of our operator. If you look at the corresponding graded sheaf of algebras, it is a sheaf of commutative algebras. So this is the sheaf of symbols. And if you look at this, this is just, you take the cotangent bundle to the flag variety, and let's denote by pi the projection. And this is pi lower star of this. So when you go to sheaf of symbols, the twist disappears. I need one more notion. I mean, if I have, so the lambda, I mean, the idea of this part is that we want to get to commutative case. We did this on the ring. We have to do it on the module. So we want to define a good filtration of d lambda module B. So there is no k involved in this. This is increasing filtration by coherent OX modules. It's a D-module filtration in the sense that Fp d lambda applied to Fq V lands in Fp plus Q V. But we want that this good filtration is as fine as possible, So we assume that if Q is large, we require that we have equality here, so that these FPs are not growing too fast. Of course, one can show that good filtrations exist. They are, of course, not unique. But if I have good filtration, I can look at the corresponding gradient module, and the gradient module is a gradient module of over the sheaf of symbols. So I have GR lambda acting on GR. Now look at the annihilator of this module. This you can interpret as a sheaf of ideals on a cotangent bundle. And look at its zeros. This is called characteristic variety of V. And using standard tricks from commutative algebra, if you analyze this, you can show that although this annihilator depends clearly on the choice of good filtration, characteristic variety is independent. So characteristic variety is some closed subvariety in cotangent bundle, which is an invariant of this coherent d lambda module. Now the miracle happens. So there is a theorem of Bernstein which says the dimension of characteristic variety is greater or equal to the dimension of X. I mean, X is the base space where you have smooth variety. In this case, there are no restrictions. Or V is 0. So characteristic variety cannot be small. So let me look at an example. For example, I believe this is an exercise. All X is structure sheaf is the X module. Characteristic variety of this is the zero section of T star X. So its dimension is equal to the dimension of X. But, for example, if I have a point, I can take a delta distribution on a point, and it generates a D module. I can multiply, I can differentiate, I get derivatives of delta function. If I multiply by regular functions, I'm going down and decrease the derivatives. So this is another example of a D module, if you calculate characteristic variety, in this case, say in dimension 1 on C at the origin, then the characteristic variety will be just at that point, you will have the whole cotangent bundle, and again, the dimension will be 1. The original proof of Bernstein, there are a lot of proofs of this fact. The original proof of Bernstein was for D modules on Cn, and it was an induction in dimension, and it was based on the following fact, which anybody who studied quantum mechanics knows, that if you take commutator of partial x, this is equal to 1. And of course, if you have a D module for D, which are differential operators with polynomial coefficients and complex line, this relation has to be satisfied. And any D module like this is either trivial or infinite dimensional, because if you would have finite dimensional representation of these commutation relations, you will get take trace. On this side, you will get 0, and on this side, you will have the dimension of the space. So it is just a consequence of this simple fact. And if we hit this minimal value, then we get holonomic modules. Which are either V equals to 0 or characteristic variety is in X dimensional. What? Module for ordinary differential operators on X. We know this, yes.
No question.
Yeah, I mean, this notion of holonomicity is local, so we can definitely forget the twists. Okay. So now let me give you the idea how the proof of finiteness goes, because this is the central issue we care about. If I take a holonomic module and I take its submodule, then the characteristic variety can get smaller only. But we have the bound on its dimension. So to make the statement precise, we have to extend this idea a little bit, like you have seen, I hope, in algebraic geometry. Define so-called characteristic cycles, which are more general, like this, they carry multiplicities, and what happens there, if dimension cannot go down, the multiplicity will go down, and multiplicity is some finite number, so if you take the subs, at some point you will hit 0, and this is the proof that this module is of finite length. Does this make sense? Any questions? I mean, this is the gist of this argument. Okay, so now I'm behind my plan, but let me try to. So this tells us what is the D module background and proving finite length of Harishchandra sheets. But I have to tell you why High-gender sheaves are holonomic. Now, if you look at the construction of good filtration, then you can see that in the case of High-gender sheaf, you can construct filtration which is by K-equivariant coherent OX modules. If you want an elementary argument for this, you can do this using tricks from algebraic geometry, or you can take your High-gender sheaf, twist it by a line bundle to get its parameter into the chamber when you have equivalence of categories. And then you can easily see that on High-gender modules there are good filtrations. That there are filtration by K-invariant subspaces, and then you sheafify this and you get a K-equivariant filtration. If you have a K-equivariant filtration, then this means that sections of differential operators corresponding to K are mapping, say, FQV in FQV. So the sections of K are in annihilator. Then you define for each orbit so you have X, you have an orbit Q, and you look at the tangent space at the orbit. And then you take in the dual space to the tangent space, you take the vectors which vanish on the tangent space. And if you look this for Q, you get so-called conormal variety attached to the orbit. And if you have finitely many orbits, each component of conormal variety is n-dimensional. Your orbit has dimension of Q, and the tangent space has this dimension, so the orthogonal piece has dimension x minus dimension of Q. So they add up to dimension of x. So the union of all conormal bundles, is something of dimension x if you have finitely many orbits. This is when finite many orbits vanish. And since the symbols of the differential operators corresponding to elements of K, if you think about, they vanish trivially and they generate the ideal which is contained in an annihilator. The zeros of annihilator must be inside this union of conormal bundles. Because an annihilator is bigger, so the zeros are inside it, but dimension is equal to dimension of x. So it's just union of components of this, and therefore dimension is equal to dimension of x, so they actually holonomic. And this completes the proof of holonomicity and the proof of finite length. Okay, now my time just expired, so I hope that I can explain today also what is another important consequence of this, and this is the fact that we can classify all irreducible Harishchandra sheets. We can give a classification of them, and this classification gives us, by equivalence of categories, classification of representations. But of course, we have to translate this into our normal language, and this requires additional work, and this is something I should discuss the day after tomorrow. I think, yeah, I don't think I will speak tomorrow. Okay, so I should. Any questions?